Hi, and welcome to Module 3 in Video Lecture 2. We're in the middle of our functions right now, talking about functions. This video, this module is examples of functions. So, if you're thinking the previous ones were too focused on definitions, you'd be in luck. This one's solely based on examples. So what we're going to do is go through a series of examples that are commonly seen in political science and social sciences more generally, discuss their properties a little bit, and a little bit where they're used. So we're going to start with the very most basic one, the linear function. The linear function is defined by two properties: additivity and scaling. Additivity means that if I add two arguments together, the function of those two arguments equals the sum of those two arguments equals the sum of the functions of each of the arguments. Scaling means that if I multiply my argument by some constant c, I get c times the function itself. A linear function looks like this, or like this, or like that. It's got to pass through 0, and it has to, for the reason of scaling, but it could have different slopes. Here, what does it look like? So it looks like this, where a is some constant. If a is negative, it slopes downward. So this is a negative a. If a is positive, it slopes upward. If a is 0, it's just 0, flat line. The bigger a is in magnitude, the steeper it slopes. A here is the slope of the function, of the line, rather. Why does this satisfy these two? We can check it out. Well, if we have x1 plus x2, we get a of x1 plus x2. That equals a of x1 plus a of x2 equals f of x1 plus f of x2, and that checks out. Or if we have this, how does that work? Well, then we have ac times x, but by commutativity we get c a of x equals c f of x, because f of x is ax, and again that checks out. So this is a linear function, and this is the general linear function. Linear functions are useful because they are the simplest function you can possibly think of. They have nice properties under differentiation. They go to a constant, and they assume nothing about risk or preferences other than assume nothing about risk or anything fancy about any details. Sorry, they assume nothing at all about the details other than sort of a base risk neutral caring about everything in the same way across the entire domain space type of thing. For instance, if your preference for money is that, means for every unit of money you get a utility of 2, an additional utility of 2. The same for $1 now, or $1,000, or $1 when you have $1,000, or $1 when you have $10,000. Right? The additional benefit of a single unit is 2. So it gives you a nice constant marginal gain for these things. So in that sense, it's sort of a baseline. There are assumptions involved in this, and we'll talk a little bit about that. But we do different kinds of polynomials. But this is a flat neutral function, and it's the most typical one you will see when you first start modeling things in game theory is this risk neutral function, linear function, because it's the easiest to differentiate. Okay. Now, you notice I didn't mention stats yet for a particular reason, which I'll mention now. That function has no intercept. This function has an intercept of b. An intercept is the point at which it intercepts the y-axis. If this is f of x, and this is x, then this is an affine function, this is an affine function, that's an affine function, that's an affine function. Pretty much anything, this is an affine function, anything, this is right here, this intercept is b. If you plug in x equals 0, you get b, so that's the intercept. These are affine functions. Affine functions are a little more general than linear functions, because if you make b equals 0, you get a linear function. So if b equals 0, then you just get this over again. But in general, so get rid of these. This is an affine function. Affine functions appear all the time in statistics because the standard linear model in statistics is basically an affine function. So for instance, if we're trying to understand, say, net immigration into a country, we might have net immigration might be some affine function of GDP, some measure of conflict, some measure of education, some measure of unemployment, and so on, plus some intercept, some baseline. So if all these independent variables were 0, what's the baseline of immigration? That's this constant here. Also plus use the error term, which we'll talk about later when we start doing calculus. But this is an affine function, and this is the most common function you'll see across stats. Now this is generally called a linear equation. A linear equation is an affine function. It's a slight complication in terms, but the importance is this is the linear model, and it's the baseline model for all of statistics that you do. And typically most assumptions on statistical behavior and hypotheses test it using a linear model. Not all, but this is the norm. Okay, so that's a function. Now, what if we move away from this? Well, we can change things. If we, for instance, think it's not that conflict doesn't matter so much at small levels, but it matters a whole lot at high levels, we might think that actually immigration responds non-linearly to conflict. So we might add a term of conflict squared. Squared terms are known as quadratic functions. A quadratic function is any function that has terms up to and including the squared term. So the most general version of this would look like this. And you saw this when we were solving quadratic equations back in the previous video lecture. This, if you can solve, if you set it equal to 0, using the quadratic equation. Quadratic functions are generally used when you believe that the rate of increase in some variable is itself increasing. So, for instance, oftentimes when you look at costs of production, you would treat them like this. Why? Because the argument is the more you produce, the more expensive it is to buy additional components in the production, and therefore each additional unit you produce gets more and more expensive. So we see a lot of times in game theory are functions of your preferences in which there's some cost or cost analog that has increasing marginal cost. And again, we'll talk more about this when we discuss optimization in part 2 of the class. But that's a quadratic function. Quadratic functions look like this. Let's draw that over again. Quadratic functions look like that around 0. You can move them up or down by adding an intercept. You can change the shape by adding the x term, and you can change the sign, whether or not it goes up or down, by changing the sign on the squared term. So this is a quadratic. This color here. This is a quadratic, and so on. These are all quadratics. Okay, so that's a quadratic. The more you can go further and do a cubic equation. So here's a cubic equation. You might guess it involves a cubed term. Cubic equations can look something like this, or whatever you want it to look like. They have multiple bends. You can have 2 different bends. A quadratic equation has 1 bend. Cubic one can have 2, or it doesn't have to. They're more rarely used. You might see them, however, in some people claim that that the proper way to measure time. The fact that time would be a cubic equation of time. You see cubic equations as well when you're trying to look at cubic splines to try to fit data. But they come up less frequently in political science than quadratics, which come up less frequently in the linear term. Okay. All of these square, linear, affine, quadratic are all examples of a larger classification of functions known as polynomials. Polynomials are like this. So I'll put a sub n plus a sub n minus 1 x to the n minus 1 plus dot dot dot. Here dot dot means continue the series. Continue the sequence onward. Plus a0. That's a general polynomial equation. That's the most general kind of equation that involves exponents on x. So constant exponents on x. Typically they're used in the same context that a linear equation is used. The linear or quadratic equations are used. They're not used that often. However, they do come up a bunch when, for instance, you're trying to approximate a more complicated function. You would use a polynomial, and again, we'll discuss that. It's a Taylor expansion. We'll discuss that when we do with calculus. For now, just know this is a polynomial. It's a general type of object. You can actually have you can make a rational function. Another use of the word rational in the ratio sense by dividing one polynomial by another polynomial. Doesn't have to be the same variable, but can. That's a rational function. And you can play around with those you want. Before we move on a little bit, let's stop for a second and define a little more polynomials, or rather exponents. An exponent, as you recall, is just the power on this variable here. So this means multiply x times x times x n times. You can manipulate exponents. If you have two x's, you multiply them together, you can add the exponents like this. And you can see that if you just go through and multiply n times and then m more times. So m times. Right, so you have n plus m more, that's n plus m, or n plus m x's. If you divide, you subtract, which means m. For the same reason, you have n, you remove m of them, you're left with n minus m. The division thing gives you a hint about a more general property, which is a negative exponent is equal to 1 over the positive exponent. That's always true. I said earlier that an exponent to the 0th power was 1. Sorry, a variable to the 0th power was 1. That's true for anything not equal to 0, but typically people will just do this, will define it this way, even though this is not necessarily true. This is necessarily true. Okay. This takes us to another type of function, the root or radical. They mean the same thing. You've all seen square roots in your life. There are also cube roots for 3 there, and so on and so forth indefinitely. A nicer way of writing these is to use just plain exponents. A square root is the same thing as writing x to the 1/2. A cube root is x to the 1/3, and a quadratic root is x to the 1/4, and so on. You compute roots by sort of inverting the exponentiation. So if you're looking for the square root of something, you try to find the number that when squared produces x. So if I want the square root of 16, what number when squared produces 16? 4. It's not always easy to find square roots, and it's harder to find cubic roots, and even harder to find quadratic roots, and so on. You generally don't have to find those in political science. Okay. One thing to keep in mind, though, in doing this is that put that back on the screen. Sorry, I had a little blip there for a second. Is that even though you can represent things like that as 1/2 and things like that as 1/3, as x to the 1/3, you can't use the same rules we did for adding exponents, for multiplying together exponents. So, for instance, x to the 1/2 times x to the 1/3 does not equal x to the 1/2 plus x to the 1/3. Sorry, plus 1/3. Rather, and you can't really combine radicals in any way, with the exception of this, if you multiply two of them together that have the same order, so they're both square roots, for instance, then you can combine the square roots together. Same thing's true for dividing. The square root of x over the square root of y equals the square root of x over y. And that's true for cubed roots and so on, not just square roots. But this is the only way you can actually combine roots or radicals together. Okay. Moving on to a couple more. Exponentiation is also common, we saw, but the actual exponential function is e to the x. Now this is different from x to the n. In x to the n, right, the variable was down here, and you were raising the variable to a set constant power. Over here, the variable is actually in the exponent. You're raising a constant e to an exponent x. Other than that, though, and this has property of looking very different from x squared, for instance, it looks like this. The exponent increases very, very, very quickly. Almost nothing increases faster than an exponent. So you use the exponent function when you're trying to increase very quickly. Most of the time the exponents come not, though, in modeling either statistically or game theory wise, but the exponents come when you're dealing with probability distributions, which often employ an exponent as part of the probability distribution function. And we'll see that when we get to the probability section. But here is how the exponent looks like. Here's how it looks. Okay, and by the way, I discovered that my ability to command the English language goes to pot in doing these things. I apologize for that. I do the best I can. But if you want these things said more clearly, I advise you to read the textbook. The main goal of this is to supplement the textbook by providing more in-depth discussion of certain topics and some more step-by-step discussion. Not to be perfectly eloquent here. Okay, so that's an exponent. Exponents, the rules for them follow the other rules. So for instance, okay, so e to the x times e to the y, e to the xy, because the e is the same in both cases. So you can get away with doing that even if x and y are a little different. So that this is a rule for exponentiation. Subtraction works the same way. E to the x y equals e to the xy. I should say, I did mention this before, x to the n raised to the mth power equals x to the n times m. Another property. Okay, that's an exponent. The inverse of an exponent is the natural log. And this means exactly what we said it meant before. The natural log of e to the x equals x. The exponent of natural log of x equals x. They're inverses. Natural log looks like an inverse as well. It looks kind of like that. Natural logs are often used quite a bit. Actually used quite a bit in political science, in both statistics and in game theory. In game theory, when you're representing utilities, you might want a utility that has decreasing marginal gain. So let's say I like money, but after a certain point I don't need as much of it anymore. Then my marginal gain for money might decrease the more I have of it. And all these terms like marginal gain we'll be discussing in much more depth in the calculus part of the class. I'm talking loosely just to give you a sense in the common English usage to understand why you would use these things. So let's say I want the next dollar I make to be less important to me than the first dollar. then I might use a log to describe my taste for money, my preference for money. Or if I believe in some statistical model that changes in, say, GDP are really important from the first, say, $0 to $1,000 per capita, but from 7 to 8,000 per capita are less important, and from 20 to 25 or 20 to 21,000 per capita are not that important at all, I might use a log of GDP to describe the effect of GDP on whatever property I care about. So logs are actually used quite a bit. Now you might ask, what about other functions for this kind of idea? Well, there are plenty of them. For instance, this is a log. I might do the square root, which looks kind of similar. That's not as... Here's more of a square root. Problem is the square root's derivative is much messier than the log's derivative, which we'll get to, so people use a log much more often. Okay, that's a log. Log has certain properties that are kind of like the inverses of the properties of an exponential. So for an exponential, we said that e to the x times e to the y equals e to the x plus y. Well, if I take log of x plus y, log of x times y, I get log of x plus log of y. So I separate them completely, actually. It is not true. This thing, that's an n. Log of x plus y is nothing. You can't do anything with that at all. Similarly, log of x over y equals the log of x minus log of y. Just like e to the x over e to the y equals e to the x minus y. And that's because e to the negative y equals 1 over e to the y. That's why that works. And finally, log of x to the b equals b times log of x. It's the last of the terms here. In the same way that e to the x raised to the b power would be e to the bx. The difference is in the log, you actually separate the logs completely. In the exponents, you just separate the arguments here, the x's. That's a log. As I mentioned earlier, that log is the natural log, base e, but all exponentials, like here's a base 10 exponential, its inverse is log base 10, and so on. So they all have their own individual logs, but you only really ever see log base 10 or natural log in practice, usually natural logs, because when you differentiate bases other than natural log, you get stuff popping out, as you'll see in calculus. But here is other logs. They look similar when you graph them. They just have different values, right? Log of 10 is 1 base 10, but it's much bigger than 10 in base e. Not much bigger, somewhat bigger. Okay, let's see. I think we're almost done with that. With this module, a couple more things to mention before we exit. One, some of these things are related. We mentioned exponentials and logarithms are related. Well, as you might have guessed already, x squared square root, when you compose those two, you get x. Here it's a little messy, you actually get plus or minus x because of the square root. So it's almost, an inverse. So they're related though. I mentioned a little bit in a previous module that if you had more than one variable, you could make functions that have interaction terms, like that. That's an interactive term between x and y. We'll discuss these more in the calculus part of the class. And finally, there are a few other functions you might see in other contexts, particularly the trigonometric functions, which you might see if you do time series. They're the most common ones, sine and cosine. Here. Sine and cosine, and they both look like this, just shifted over to various points. You won't deal with these very often unless you actually are taking trig, or dealing with triangles or whatever, but in practice in political science, you'll generally be dealing with these in the context of like time series and stuff like that, and you can talk about more there. I'll give you derivatives of these in the calculus part of the class, but again, you don't spend too much time paying attention to trig functions. Okay, so there's a not so quick run through of a bunch of functions you see often. The next module, we will finish off our foray into functions. Thank you very much.